Up next, reactions of ethers. Ethers, like alcohols, don't have a good leaving group. Ethers do not do SN1, SN2, E1, and E2. They only do substitution reactions. Ethers do not do eliminations. Ethers only react with acids like these, HBr, HCl, HI. So, ethers cleave in acid to split the ether into two separate pieces. If you're methyl primary secondary, you do SN2. If you're tertiary allylic benzylic, you do SN1. What the heck does that mean? Well, first of all, we have an acid. We have a bad leaving group. Let's protonate to make a better leaving group. Like so. OH plus. From here, you have a decision to make. We need to consider both sides of the ether and see what each side would say to do. That side of the ether, that carbon that's connected to my ether, is a secondary carbon, but it's an aryl carbon. Okay? This other side, over here, that carbon is a primary carbon. It's not allylic, benzylic, aryl, vinyl, nothing special. So, according to my list, it says secondary goes by SN2, but aryl is not on this list. Aryl does not do substitution, so we're not going to bother this blue side whatsoever. My list says primary wants to do SN2. So what that means is the primary side gets SN2'd upon and lets go of the oxygen. Let me show you what I mean. We've got Br minus still hanging around. Br minus attacks the side that's ready for SN2 and lets go of the oxygen like that. So we end up with a Br connected to my primary carbon and this OH. Yep. Since we said one equivalent, that's finished. I've got more to say, but we're going to move on to the next example, and I'll come back to explain a little bit more. We did SN2 in this reaction because the primary carbon said to do so. The aryl carbon does not do substitution, period. More examples. Hold on. Next, we have an ether. It's got a bad leaving group. We protonate it to make it a better leaving group, like so. And we evaluate our two sides. The blue side, the carbon that's connected to the ether, that blue side is secondary. No allylic, benzylic, aryl, vinyl stuff. The other side, the green side, that carbon that's connected is a tertiary carbon. So tertiary says, let's do SN1. And the secondary side says, let's do SN2. Uh-oh. We have a disagreement. Blue side says do SN2, green side says do SN1. When your two sides disagree, when it's SN1 versus SN2, your two sides disagree, make a carbocation. So that means we're going to do SN1. So how does that look, SN1? It means let go of the side that will make the best carbocation. Just let it go. D believes. And you have this tertiary carbocation. That tertiary carbocation, oh, it's going to be a little crowded. We'll erase. That tertiary carbocation gets attacked by bromide. Bromide attacks that tertiary carbocation. We end up with these two products. So when you cleave an ether, you will always make an alcohol and an alkyl halide, because remember, you're always using an acid halide to cleave them. So as long as you've got one equivalent, you're always going to make an alcohol and an alkyl halide. Why does one equivalent matter? Do alcohols react with acid halides? Like, would this alcohol react with an HBr if you had a second equivalent? Yeah, it would. So alcohols could react again. Let's come up with another color. If you had excess HBr you would undergo another SN1 mechanism to give you that purple alkyl halide. Okay, one thing that I think is worth pointing out, secondary alcohols do SN1. Secondary ethers do SN2. I'm going to repeat that, even though you can rewind. Secondary alcohols do SN1. Secondary ethers do SN2. So even though this side was secondary in an ether, it would say do SN2. Now that this side is an alcohol, it would say do SN1. So be wary of that. Otherwise, the groups agree. Tertiary allylic benzylic alcohols do SN1. Tertiary allylic benzylic ethers do SN1. Methyl primary alcohols do SN2. Methyl primary ethers do SN2. Okay. I said we'd go back to the one equivalent back here. This is an aryl alcohol. That aryl alcohol does not undergo substitution. So even if you had excess you would get the same products. Even if you had excess HBr, this is all you get. Because aryl alcohols do not undergo substitution. Okay. So that's our first two ether examples. The first one was no reaction side versus SN2 side. We did the SN2. This second example is SN1 versus SN2. Make a carbocation. This last example, we're going to start out by protonating our ether with our acid to make it a better leaving group. Plus our two sides. This side is primary. It says SN2. This other side is secondary. It says, ooh, SN2. Both sides agree that we're going to do SN2. Let's do SN2. But when it's SN2 versus SN2, you have to figure out which side you actually do the SN2 on. You attack least crowded, because the least crowded side is the best for SN2 substitution. And the least crowded side for us is primary. So bromide attacks that primary carbon, and lets go of that O. We get these two products. If we had excess HBr, yes, that alcohol could be substituted, but we've only got one equivalent, so we get those blue circled products as the only products. Ethers are cool questions, in my opinion, because you have to choose which side to obey and then do the right mechanism accordingly. You got to choose and then do the right thing. It's a good question. You get that hint that I'm dropping there? Yeah, okay. Ethers do not do elimination reactions. Ethers do not do anything besides the reactions I have just shown you. SN1 and SN2, and they cleave with acids like HCl, HBr, HI. That's all they do. Because that's all they do, they're usually used as solvents because they don't really participate in reactions. They can be around to make everything soluble and dissolved and happy to react together, but they themselves don't participate. So in all of 10 minutes or less, we have talked about all of the reactions that you have to know about ethers, with one exception, and that's epoxides. Coming next. Hold on. Ethers are good solvents. Crown ethers, that's this thing, are good to help facilitate other reactions as well. So crown ethers are things like this that have a cavity in the middle of them where you can get interactions between things like a potassium cation and your crown ether. You can have crown ethers of a lot of different sizes, and based on the cavity size, it can bind different sort of cations. So this black one is a 15 crown 5. That's telling you it's a 15-membered ring overall. It's a crown ether, and there are 5 oxygens in that crown ether. The blue one over here would be a 1, 2, 3, 4, 5, 6, 7, 8, 9, a 9 crown 3. 9 crown 3 is going to be a smaller cavity in the middle, fits a smaller cation in there, and help facilitate other reactions based on that. If you read about them on this page, it talks about how a lot of SN2 reactions, you add in a crown ether to help distract the cation so that the anion, whatever anion is attacking, sulfur is one of my favorite anions to attack in SN2, you attach a crown ether to the cation so that the anion is freely available to go do the attacking, to go act as a nucleophile. Oh, tripping over all my words. Yep, crown ethers, they're kind of cool things. Ethers are also common in antibiotics. That functional group is a very common antibiotic group. Yeah. Ethers not very reactive, but useful in a lot of other contexts also. The one category of ethers that are very useful and can do a lot of different reactions, well, they can react with a lot of different things, but there's still only one style of reaction they do, is epoxides. Epoxides, let's remind you how to make epoxides. We've talked about 2 ways to make epoxides, these 2 ways. You can have an alkene that you add a peroxy acid to. One of our favorite peroxy acids is MCPBA. MCPBA reacting with that alkene makes an epoxide. I chose this E-alkene, this trans alkene, so that we could show proper stereochemistry over here. And one way to show stereochemistry is put the epoxide in the plane, like I have done, and put the dashes and wedges on the H's and the methyls. Epoxidation is a syn addition when you add peroxy acids. That means that stereochemistry of the other groups are retained. So these methyls are pointed opposite directions now because they were pointed opposite directions previously. These hydrogens are pointed opposite directions in the beginning, so they have to stay pointed opposite directions. This is the appropriate epoxide with stereochemistry when you add MCPBA to that trans 2-butene. Yeah. Could you draw the epoxide products a different way? Yeah, you could. It's a little bit weirder maybe, but you could draw your 2 methyls, your methyl and hydrogen as having dashes, the methyl and hydrogen that I gave a dash, and your epoxide as having a wedge, and then your methyl and hydrogen down at the bottom are in the plane. It's not as common, but it's possible. Both of those are rings, so it's not maybe appropriate to say what I'm about to say, but both of those are an eclipsed conformation. They're not staggered, but that's okay. It's good. I like it. All right, so that's if I add a peroxy acid. This other method says I can have a halohydrin plus base. What is a halohydrin? Halohydrin is a halogen directly next door, vicinal to an alcohol. A halohydrin would need to have this anti-stereochemistry shown, and we add a strong base, like one of my favorites is sodium hydride. The purpose of that strong base is to grab a hydrogen from your kind of acidic alcohol to make an O-. And then you do an intramolecular SN2, like that. And we get an epoxide. The epoxide has to always have syn stereochemistry in the end because you can't have a 3-membered ring pointed 2 different directions. It doesn't work like that. Why did I start drawing that thing in the middle? Because I wanted to show you that both ways to make epoxides really starts with an alkene. Yes, this one said an alkene plus peroxy acid because that's making an epoxide in one single step, adding a peroxy acid like MCPBA. But if you have an alkene and you turn it into a halohydrin, then you add base, you can turn it into an epoxide. So it's a two-step way to make an epoxide. They're equally good. You just got to remember that you add Br2 and water to an alkene in order to make the halohydrin. Both of them valid ways to make epoxides. We got to know both. Okay. Epoxides, how to make them. Epoxides, what they do. The ring gets busted open. Have you ever seen a three-membered ring get busted open? Maybe like a halogen three-membered ring, like a bromonium? Yeah. Have you ever seen a three-membered ring get busted open, like maybe a mercurinium three-membered ring? Yeah. Epoxides are three-membered rings that get busted open. They all do SN2. No SN1, no E1, no E2, always SN2 with epoxides. Because you're busting open a ring, you get anti-addition. Have you ever seen a three-membered ring get busted open and give you anti-addition? Like maybe, I don't know, a bromonium, maybe like, I don't know, a mercurinium? Yeah. You ever seen a three-membered ring get busted open and give you anti-stereochemistry? Yeah. The regiochemistry is different if you're under acidic conditions or basic conditions. And really, I should maybe even say if you're under acidic conditions versus neutral conditions, because generally if you're under neutral conditions, you're going to do the same thing as if you're under basic conditions. We'll explain with more examples, more details momentarily. Here we are. Examples. I have an epoxide. The first question I ask myself is, are these reagents things that tell me this is under acidic conditions or basic conditions? And I see sulfuric acid, so I've got acidic conditions. Epoxides are ethers. Ethers don't have a good leaving group. So if you have acid, the first thing you got to do is protonate that ether to make it a better leaving group. Like this. We've got a three-membered ring with a heteroatom with a plus. Have you ever seen a three-membered ring with a heteroatom with a plus? Have you ever seen a three-membered ring with a heteroatom with a plus? Yeah, we've seen them 3 times now. A three-membered ring with a heteroatom with a plus. When you bust open that bromonium, did you attack the less substituted side or the more substituted side? When you busted open that mercurinium, did you attack the less substituted side or the more substituted side? Well, let's bust open this bromonium and this mercurinium with water. We're going to bust it over here. We're going to bust it over there. Why do we bust it that way? Because the more substituted side has better carbocation character. When we have a positively charged intermediate, like these, we're worried about carbocation character. Is it a legit carbocation? Absolutely not. But when we have a positively charged intermediate, we're worried about carbocation character. So we attack the most substituted side because that side has better carbocation character. You follow? We attack the most substituted side because that side has better carbocation character. So we worry about stereochemistry a bit here. That methanol attacked, and when it attacked, it brought with it a hydrogen and a methyl. And we need to do inversion because we're doing SN2. We need to do inversion at that center where we attacked. Well, my epoxide was in the plane pointed up when I let it go up here. My methanol I'm showing in the plane pointed down. Letting go of my leaving group pointed up. Incoming nucleophile pointed down. That already shows me inversion. So that means that my ethyl stays wedged and my methyl stays dashed. I will recap that with R's and S's. I will say more about that with R's and S's in one moment. Let's finish out this mechanism to get us a final product because we're not done yet. Methanol comes to clean up. Clean up, everybody clean up. And we get this product as our final product. Yep. Double check with R's and S's that it really has been inverted. Priority number 1, 2, 3, 4. 1, 2, 3, 4. Lowest priorities in the back. This is S. At the bottom down here, 1, 2, 3, 4. 1 to 2 to 3. Lowest priority in the back. This is R. We properly inverted that stereocenter. Why does it matter that R becomes S and S becomes R? The leaving group was my highest priority, and my incoming nucleophile is my new highest priority. When your priorities don't change like that, leaving group number 1, incoming group number 1, when your priorities don't change like that, that means R should become S and vice versa. Yep. If we made this one little layer of complexity heavier, put a little methyl over there, make that carbon asymmetric, shouldn't that carbon stay wedged the whole time? Heck yeah, it should, because you never attach carbon number 2. It's not really carbon number 2. I saw that and said that, but that priority number 2, that carbon. You never attach that carbon, so that carbon stays the same. Yep. That's if you're in acid. What if you're not in acid, like this bottom example? The first question you ask yourself about an epoxide reaction is, am I in acid or neutral or base or what? This, I would say, is basic. When it's basic, you don't do the same thing you do in acid. Give me a second to clear this off. Hold on. Okay, so in base, you are not worried about carbocation character. In base, you're worried about accessibility. Where can I attack and where can I attack right now? I am itching, ready to attack something. In base, you attack the least substituted side, like so. And I'm going to go ahead, and it's real illegible over here, but I'm going to go ahead and put a wedged methyl over there. I want to point to that direction because. Going to put a wedged methyl over there like that purple one up top so that we can talk about inversion. I'm doing SAN2. My OMI is now pointed down, and my epoxide let go when it was pointed up. OMI pointed down, epoxide was pointed up, and it let go. My wedge stays the same over there. That wedge staying the same does show inversion. I promise. We'll confirm with R's and S's momentarily. This wedge and dash also stays the same because that stereocenter did not get bothered. That stereocenter did not get attacked. We get this product. We don't usually make a neutral, we don't usually make a charged final product, so we neutralize it, and we get this. What's the main difference in these two molecules? Well, one you busted open on the most substituted side, this one. The other you busted open on the least substituted side. The regiochemistry is different when you change from acid to base. In acid, you attacked the most substituted side because you had a positively charged intermediate. You were worried about carbocation character. In base, or neutral conditions, lack of acid conditions, you attack the least substituted side because you're going for the least crowded, the most accessible side. You're ready to attack and attack quickly. So in base, or lack of acid conditions, you attack the least substituted side. In both of these reactions, we did SAN2, and we got inversion at the carbon that was attacked. We're not going to talk about a ton of epoxide examples. We are going to do a couple more. But we're not going to talk about a ton of epoxide examples because, number one, we know that epoxides always do SN2. We can give you a ton of different nucleophiles here, a ton of different reagent conditions and the epoxide should always do SN2. The big deal is knowing whether it should attack the most substituted or least substituted side, but regardless, it's always going to give you inversion at the center that got attacked. It's always going to give you an anti-addition overall, the leaving group, the O, of your epoxide, and the incoming nucleophile, whatever the heck it may be, gives you anti-stereochemistry. Yeah? We talked in the last video about cholesterol. This is part 2 of the biosynthesis of cholesterol. We left off with making squalene. Squalene was long and stretched out in our previous picture, but now it's all bundled up like this so that we can more easily say when squalene epoxidase, an enzyme that turns this alkene down there into an epoxide, squalene epoxidase. This enzyme into this alkene into an epoxide. It goes through this kind of cascade-looking reaction biologically, crazy, I know, to give you a carbocation up there. When you draw all those arrows, this carbon is going to end up positively charged. There it is. This steroid, this 666 5-membered ring, that's a steroid. And cholesterol is a steroid. So is testosterone and estrogen and a ton of other hormones in our bodies. All of those hormones come from squalene. Our body and plants and stuff synthesize tons of hormones and steroids from squalene. So, squalene epoxidase makes an epoxide through this cascade, and then just a few short steps, you end up with cholesterol. All of those steps we're not super worried about. It's just cool, I think, to show you how epoxides really are things that our bodies make. They look super unstable, but they're useful for a lot of things. All right, that's enough of a hiatus.